Lior Alon, MIT, who will speak about nodal count statistics, universality, from quantum graph to random matrices. A large program.
Thank you very much. Thank you for the organizers for giving me this great opportunity. So far, it has been the greatest conference I've been in. It was truly amazing. Not thank you for putting me in the same day with such great speakers. It makes me, but it gives me a good excuse why my talk was not that good. Just always comparable. Before that, I'm actually going to suggest universality, but also confront universality. So the title might be a bit misleading. Maybe I should have a question mark here. I'm going to talk about nodal count statistics, universality, from quantum graph to random matrices. This is all funded by the Simon's collaboration on localization of waves. I'm going to talk about several works from span over 10 years with all of these great collaborators. Gregor Berkolaiko, Rami Band, Mark Goretsky, Dan Mikulincer, and John Herschel. And these are just a list of the papers I'm going to mention. And I'm going to do a brief motivation from a nodal statistic from a quantum chaos point of view, then present the quantum graph and the universality conjecture. From there, I would go to operators on discrete graph, finite graphs, from there to matrices, and to randomly signed matrices. And finally, I hope I'll manage to have the time to talk about very, very recent works on nodal count for GOE matrices and orthogonal invariant ensembles, and even work in progress on phase transition of nodal statistics for the Rosenzweig-Porter model. But first, as we all know, in dimension 1, already 200 years ago, Sturm showed that if we have any Sturm-Liouville operator on an interval, the kth eigenfunction has exactly k minus 1 zeros. More than 100 years later, Fiedler showed that also if we take the Laplacian on an interval, finite, a discrete Laplacian, so it's just a matrix, the kth eigenfunction, now it's a vector. It usually doesn't vanish on the nodes, but it has k minus 1 sign changes. And this is going to be a common thing we're going to talk about. But when we go beyond the dimension 1, now we have nodal set, so it's a codimension 1 manifold or variety, and it's no longer counting points, so what can we count? So it can talk about the d minus 1 dimensional size of the nodal set. We can count about the number of connected components after we remove the nodal set, what is left. Both have amazing result and a lot of open questions about these kind of questions. First of all, the first question people ask is how does it grow as the eigenvalue grow? And already 100 years ago, Courant and Hilbert showed that the number of connected components is actually bounded by the spectral position of my eigenvalue. And later on, Pleyel, and we have Yosif Polterovich here as the expert, showed that this bound is actually attained only finitely many times. And it's interesting to talk about the statistics of these numbers as they grow. And something very interesting that will be related to what I'm going to talk about later on is that the difference between the number of connected components and this upper bound was shown by Helfer and Thomas Ostenhoff to be related to some topological quantity of some critical points of functionals. The next question that someone can ask, and this is now getting to the realm of quantum chaos, is how does it fluctuate? These sequences fluctuate around the growth. And again, okay, so here I forgot to mention that this size of the nodal set grows like the square root of the eigenvalue. This was a celebrated conjecture by S.T.Yao, proved by Donnelly and Pfefferman for real analytic manifolds with for analytic manifold with analytic metric, and the celebrated work of Eugenia Malinkova and Sasha Lagunov took it down to almost prove it completely for C-infinity manifolds. And, oh, sorry. And now, after talking about the growth, I want to talk about the fluctuations. And we already heard about the Berry's random wave model. And the heuristic beyond Berry's random wave model says that, well, these quantities should somehow fluctuate in a Gaussian manner. So what is the setting of interest in this case? So we start with usually the chaotic deterministic case, where we have a sequence of eigenfunctions going to infinity, and we believe that it should locally behave like something random, like a random wave, which would somehow suggest that the fluctuation of these quantities should fluctuate in some Gaussian fashion after you normalize it correctly. But as Maxime already did a great job in introducing, sometimes when we cannot get access to chaotic, we get access to random eigenfunctions from very high multiplicity. And there was the beautiful works of Sodin Azarov on the sphere, and then of Rudnick and Wigman on the torus, in which these properties were shown to actually be to fluctuate in a Gaussian manner. And lately, Igor Wigman showed that actually, if we change the torus and look at different type of tori, then the fluctuation of the side of the nodal set failed to be that Gaussian that we expect, and kind of called it the lack of universality. And this is the type of question I'm going to ask, but I'm going to talk about a completely different model suggested by Uzi Smilansky, and that's the limit of large quantum graphs. Again, this is Maxim already did a good job explaining quantum chaos, but I always like the Tolstoy, all happy families are alike, each unhappy family is unhappy in its own way, and as a person studying quantum chaos, happy family is chaos, and all chaotic families, when we zoom in, look the same. And each integrable system has its own characteristic.
But they're not unhappy.
What?
They're not unhappy.
The people studying them are.
So, start with some famous conjectures. This is what I like to call the Nodal BGS conjecture because of Bloom, Gnutzman, and Smilansky, and because we also have Bogomolny and Schmidt, and this is from the original BGS conjecture, which suggested that if we have a Dirichlet problem of a chaotic domain, where the billiard is chaotic, the fluctuation of the nodal count and the fluctuation of the nodal set in the right scale should have Gaussian behavior. And a year after that, Smilansky, who was dealing with quantum graph at that time, went on to look at this kind of easier model, and always we're taking quantum graph with incommensurate edge length, and he was looking at the fluctuation of the nodal count and saw that they have Gaussian behavior, and he conjectured that this should be the case as we take very large graphs. So what do I mean by a quantum graph? So the word quantum, except for like, it's there mainly to get budgets, but we're talking about a simplicial, one-dimensional simplicial complex. So functions get their values along edges, we have a bunch of edges that we glue according to some graph structure. And we're looking at Laplacian on that object. And we need some vertex conditions. So these edges should know, the function on the edges should know about each other. At the vertex, the function should agree. And the sum of the derivatives should sum up to 0. And we should take derivative with respect to, say, all incoming or all outgoing. And in this case, we have a coupled ODE. We're asking for a solution for this ODE with these vertex conditions, where we have the same eigenvalue, kn squared, in all of the edges. And just to make sure, I would always assume that my edge length is incommensurate, and by incommensurate, I mean linearly independent over the rationals. So this means that the inner product of L with Q is non-zero for all rational vectors which are non-zero. And this is what makes my system almost chaotic. So once I have a quantum graph, I have a function. Usually that function doesn't vanish on vertices, and usually my eigenvalue is simple, so I can define my nodal count, phi k, just to be the number of zeros of this function. Now, I'm going to repeatedly refer to the nodal condition. So when I say nodal condition, I mean lambda k is simple, and fk v is non-zero for all v vertex. Now, I'm going to put this high so that I don't touch it. And that's there to stay. And the question of whether this is generic and in what sense it's generic, I have a paper that I really like about it, but unfortunately I don't have the time to talk about it. But it's very much influenced by the work of Hillard and Lenny Friedlander. I'll be happy to talk about it later. So under the nodal count condition, Berkolaiko proved that this quantity is always bounded between k minus 1. This is what we had from Sturm. And k minus 1 plus a small number. So this is a fixed number, and k goes to infinity. So it's a very good bound. It means that asymptotically I know exactly what happens, and this is the level of my fluctuations. So my fluctuations are just subtracting k minus 1 from these leading terms. What is beta? So beta is my first Bethe number of the graph. It's a topological quantity. It's defined as the rank of the first homology group, or the measure of space of cycles. But in layman terms, it just means number of edges minus number of vertices plus 1, assuming that the graph is connected. So if we're just looking at this, we see 1, 2, 3, 4, 5, 6 cycles. Beta is 6. And this is a tree, no cycles. And that's a definition. A graph is a tree if it has no cycles. Now we can talk about these fluctuations. So given a standard quantum graph, I have this sequence of nodal surplus, these numbers that are bounded between integer between 0 and the first Bethe number. And I can talk about, the distribution of these numbers. So I would just put delta masses on them and take it to infinity. But this is the same as just taking the histogram for the first capital N, normalized, and then take capital N to infinity. And it's a priori not even clear that this is well defined. So the first thing that we did was proving that it's well defined, so that this, as Semyon already mentioned, this will always have several limits for the subsequences, but showing that the sequence converges, it's a thing, and we proved it. And not only that it's well defined, it is symmetric around beta over 2. So if we just sum these numbers, knowing that we're going to get a half integer, we can just sum finitely many and see it converging. We're going to know what is the Betti number of the graph. So this is a spectral data that gives us some topological quantity on the graph. And the proof relies on two ingredients. The first, as always happens in chaotic system, is ergodicity. The second, which is very much influenced by Helfer's work, is Berkolayko's nodal magnetic theorem. And in order to explain what's the ergodicity here, I'm going to do it in an unusual way, not through the equations, because it's too late and we're all tired. So let me just draw some picture and show you a nice animation. But first, let's notice something. So if K is in my spectrum of gamma L, and I have my eigenfunction, so that's a bad color. Let's do yellow. Okay, so I have my nice eigenfunction. Obviously, on the edges, my function on an edge, it's one dimension, so it just looks like A cosine kx plus B sine kx. And the main thing is what is A and B. And there are two things that we can immediately see here. One is that, so K is in the spectrum if and only if Tk is in the spectrum of gamma 1 over TL. So this is standard scaling. Yeah?
Can you recall what the boundary at the ends of the...
Neumann, it's either Neumann or Dirichlet, but the only thing that I care about is that it's scaling invariant. So it's either Neumann or Dirichlet. So because of the scaling invariance, I know that I can just scale. So this means that the vector KL, which is just KL1 up to KL number of edges, this vector is invariant to scaling. Okay, what else do I know? So what happens here? This is a wavelength, 2 pi over k. So this means, I'm not calculating my board correctly, unfortunately. Let me do it. This means that the map that takes KL, so again, I'll do it here. KL is this vector, KL1 up to KLN. And the map that takes KL to KL plus some 2 pi over K Z something in Zn. For a moment, let's forget about negative edge length. So positive. So this map, right? Also doesn't change my spectrum for K. Because if I just remove this part, I still have my eigenfunction satisfying the vertex condition with the same eigenvalue. So this conclusion means that the quantity that I care about is KL mod 2 pi. So that means that here I need to have this thing. I hope that my hand waving was convincing. So now, remember we have a sequence of eigenvalues. Let's see how these numbers, these vectors in a torus look like. So let me just plot. I'm taking a star graph. I'm taking two choices of L1, L2, L3, and I'm just plotting these vectors for j goes from 1 to n, and n is running. And you can see here how these points start to equidistribute along a given manifold, or variety, because we have singularities. And what you can also see is that although they equidistribute in a different manner, so with a different measure, the variety is the same. The variety doesn't care about the edge length, the measure does. And this is the thing which I'm going to exploit. So let me write it here. I'm going to have some variety that only cares about k in spec of gamma L, L in R plus N. So all the possibilities that I can get, and what we show, it's a theorem by Barat and Gaspard, a quasi-theorem because they're physicists. Later on, people like Gregory Berkolaiko and John Keating wrote it properly. The set of points, so if I take J and I map it to KJL mod 2 pi, assuming my edge lengths are incommensurate, assuming L incommensurate, this sequence equidistribute in sigma according to a measure, we call it the Barat-Gaspard measure, that depends on my edge length.
So I think you need to take the closure to define sigma and gamma.
No,
And then,
because this is for all. It's not for one, it's for all.
then I'm very confused. I think you want to fix L.
No, I'm saying it's a property of the graph, regardless of the metric. I'm saying give me any metric of the graph, and compute the spectrum.
Okay, I'm confused because usually you would start with a variety, a subvariety of the
So,
torus, and then
let-
you know about K.
This is the same as writing L in 0 to 2 pi to the E, such that 1 is in spec gamma L. And I can just I can define it using equations as well. I'm trying to avoid that. But that's why, because I have for any KNL. That's my moduli space. With this in hand, the proof of convergence becomes just whether I can measure the nodal surplus on this moduli space. And once I show that I can measure my nodal surplus on this moduli space, and it's a nice enough function so that these are measurable sets, then just taking the set in my moduli space on which sigma k is equal to j, and taking the measure of this set gives me my limiting measure. Now, not a lot of calculation there, up to the fact that we need to explain why this can be interpreted as a function of these guys. And for that, I actually have 3 proofs for that in my PhD thesis, but originally we used the nodal magnetic relation. So if I insert magnetic field, it actually only depends on the flux along cycles. And because I'm on a graph, I have a finite dimensional space of cycles. So I have a beta dimensional torus of parameters, my magnetic potential parameters, and my eigenvalue, every eigenvalue, so the lambda k was my, or kk was my original eigenvalue, and now I can perturb it using this using the magnetic field. It becomes a function of these magnetic parameters, and the theorem is that assuming the nodal condition for lambda k and its function, then uk extend analytically around 0. It has a critical point at alpha equal to 0, just by the symmetry of conjugation. This critical point is non-degenerate, and I can talk about its Morse index. And surprisingly, the Morse index of this critical point is the nodal count deficiency, the nodal surplus. So this is why I can read it off here. So that proves that we have a limiting measure. How do we prove that the limiting measure has the symmetry that I talked about? So now we just need to find a measure preserving map that takes sigma to beta sigma equal to j to sigma equal to beta minus j. And once we have that measure preserving map, which essentially this measure preserving map, this is for you, this measure preserving map is taking you from alpha equal to 0 to alpha equal to all pi. And surprisingly, alpha equal to all pi can be realized as a different point here, and it's measure preserving. So it inverts my Hessian, which inverts the index of the Hessian. And this proves that that it's symmetric around beta, a beta over 2, so the expected value is beta over 2. But we managed to show more than that, which led us to the conjecture. So this is just a reformulation mathematically of Smilansky conjecture. And the conjecture now is that for any standard quantum graph, gamma L with incommensurant L and first Betty number beta, the distance, so I'm getting a Kolmogorov signal distance between my nodal surplus and a Gaussian of same mean and variance, go to 0 uniformly over all of my possible choices as beta goes to infinity. And not only that we have this conjecture, we can prove that it holds for some families of graphs. So if the graph has disjoint cycles, the magnetic perturbations are independent for independent cycles, and then up to a lot of mathematics, I can show that it's just like like coin flips independent of each other, so the distribution becomes binomial. And binomial is as close as it gets to Gaussian. After that, we wanted to take cycles close to each other, and we went to these two families of graphs. For these two families of graphs, we managed to actually prove it, but not far beyond that. So here we have binomial plus some bounded arrow, still goes to Gaussian. After that, we said, okay, it's very clear here that the edge length doesn't play a significant role. It's kind of how we sample things on the manifold, but the significant role is the manifold and its partition. So we remove the L dependence. How do we do that? So these measures are convexly dependent in L. So this means that the measure of my sets that determine the nodal distribution is actually living in a convex Hall of certain points. Now remember, I'm only allowed to take L in commensurate, but here, to get from here to here, but here I can take L to be whatever I want. So here when I take L to be whatever I want, I can get all the way, I can plot L equal to only the 1 at edge number 4 and 0 otherwise, and I get W4, W1, W2, W3, and it's going to be in the convex Hall of these guys. And not at all trivial, because this is not at all a convex function, the supremum gets its highermost point on one of these vertices. So to prove this, I don't need to go over all possible incommensurate edge length. It's enough to just check my the number of edges distributions. And we did that. So take complete graphs of larger and larger graphs, and you can see that it becomes a nice Gaussian. Take ladder graphs, larger and larger, it becomes a nice Gaussian. Grid, square grid that I glue periodically. Remember, everything is going to be edge lengths that are incommensurate, but I already went to the moduli space, and it becomes Gaussian. Random Erdős-Rényi becomes Gaussian. And moreover, if I plot all of them, and I also took random regular graphs of degree 3, 4, 5, and for all of these, for all of my choices, if I plot the worst case, and the case distance to Gaussian, I can see it decaying as beta goes to infinity. And it's very convincing evidence. But this is where we got stuck, and at this point, Berkolaiko kept pushing me to try to work with discrete graphs and matrices. And the nice thing about discrete graph and matrices is that on one hand, I get to play with graphs. On the other hand, everything that we discussed so far can be realized or can be approximated by a matrix on a discrete graph. Any elliptic operator on a manifold can be approximated by a discretization of the manifold. Eventually, if my mesh is fine enough, I will be able to capture I will be able to capture the behavior of nodal sets. There are a few problems here. So what's work and what doesn't work? What does work is that I still have the Berkolaiko bound, and I still have the nodal magnetic theorem. However, and this is getting me back to Maxim's talk, when we're in a quantum chaotic situation, we have eigenvalues going to infinity, and we have ergodicity. And in that case, my beta is fixed. My beta is fixed, it's a small parameter, I have small fluctuations, spectrum goes to infinity. And moreover, in that case, nodal domains and counting zeros is pretty much the same thing. So except for a few finitely many eigenvalues at the bottom, this equation holds always, and it's the same statistics. When I go to discrete graphs, I'm in a completely different situation. So my k goes only up to n, my number of vertices. However, my Betty number can be as large as n squared. So suddenly this bound looks horrible. So suddenly this bound tells me that I'm bounding, so suppose that I'm looking at a 1000 by 1000 matrix, and my beta is of the order of million. And here I'm saying I have some quantity which is bounded by, I don't know, 100 and 100 plus a million. That's horrible. Another thing is that I no longer have ergodicity. So this is usually, again, going back to Maxim's talk, where we need to push a bit of randomness. So it's a random in, random out. We don't get to ergodicity in, random out. Okay, so to go to the graph setting, let me go back to Fiedler. And I kind of gave you a miniature of his theorem here. So it's not only that he showed that the k is eigenfunction of Laplacian on a finite graph has exactly k-1 sign changes, he showed that whenever G is a finite connected tree, LW is any weighted Laplacian, V is any real diagonal, and A is a weighted Laplacian plus V diagonal, the kth eigenfunction has exactly k-1 sign changes. What do I mean by sign changes? Just count the number of edges on which the kth eigenvalue changes sign. And that's exactly k-1, of course, assuming nodal condition. But I even do something better than that. Why stop at these matrices? So whenever I have real symmetric matrix, I can think about it as an operator on a sign graph. So if I have an n times n real symmetric matrix, the graph of A is a graph of n vertices with edges which are exactly given by the non-zero off diagonals. So I don't care what happens on the diagonal, but just reading the support of the off diagonal, I construct a graph. And this matrix is an operator on this graph. And if all of my off diagonals are negative, if all of the off diagonals are negative, I'm in this situation. I can always write it like that. But if my off diagonals are positive, I can think about it as adding a sign, assigning a sign to my edge. So this means that it has no signs. And in general, the sign would be minus the sign of the off diagonal edge. In this case, instead of defining number of ij edges such that the eigenfunction changes sign, I can write number of I less than j such that aij, fki, fkj is bigger than 0. And it's exactly the same thing when I'm getting back to this Schrödinger type matrices. So this is the quantity that I'm going to keep using. This quantity, by the way, is gauge invariant, which is very important. So the most general theorem of Fiedler is saying give me any n times n real symmetric matrix for which the graph is a connected tree. Assuming nodal count condition, the nodal count is exactly k-1 for all k. And it is a very strong thing, so strong that Rami Band, my PhD advisor, proved an if and only if. So assuming that you have the nodal count condition and the nodal count is k-1 for all k, the graph must be a tree. And again, we have the equal theorem. And again, we have the nodal magnetic theorem. So let me stop here for a minute and just define what's magnetic field for a matrix. So if A is a matrix on G, real symmetric, alpha, my magnetic parameters, a priori alpha lives on the torus of edges, and my matrix A alpha is going to be Hermitian matrix that equal to A ij if I equal to j, and equal to alpha ij aij if ij is an edge, and I kind of need to choose orientation to make it Hermitian for the other direction. Let's do it like that. Sorry. Let's say it's going to be ARR when I equal to J equal to R. It's going to be ARS when RS equal to IJ, an edge. And it's going to be A bar RS when Rs equal to Ji, just the inverse in H. So this is just makes this matrix a Hermitian matrix. This is the action of magnetic field, and claim this is gauge invariant. I only need alpha on a beta dimensional torus, choosing one edge per cycle. So for example, I can take G without a spanning tree. And once I have that, I have my nodal magnetic theorem. So it's due to Bercolayco. Colin de Verdier saw it and gave even a much better proof, although it was Bercolayco's idea. Mark Goretzky and I essentially didn't contribute much, but we expanded it from discrete Schrödinger operators to all matrices. But the theorem says that if lambda k of A alpha satisfy nodal condition, then alpha is critical point if and only if all of these quantities are real. So I can even talk about counting their sign changes, and it is non-degenerate, and sigma k equal to the Morse index of lambda k alpha. Let me put it up. And with this, we were able to show some nice things. So the first conjecture that we had was that the distribution over all eigenvalues should be close to a Gaussian run beta over 2, as we had for the case of quantum graphs. And this was what Bercolayco thought, was what Smilansky and many other people thought, until Urshel and I proved the following bounds. So the average nodal surplus is bounded below by beta over n and above by beta minus beta over n. But not only that it's bounded, it's tight for all n and beta. In particular, it's very far from beta over 2. So again, think about beta as being a million, where n is 1,000. So this would be 500,000, and this would be 1,000. The main idea we have, the main idea for the bound is very cute. So just by the way that this is set up, the diagonal terms of the matrix doesn't change by magnetic perturbations, so the trace doesn't change. So if we sum the eigenvalues, it's not dependent on the magnetic field, which means that if we sum the Hessian of the eigenvalues, they sum up to 0. and each one of them has a non-zero determinant. So now there's a question of, okay, I given n beta time beta matrices that are invertible. I know that they sum up to 0. What can I say about the sum of their indices? And this is kind of a generalization of given n non-zero number that sum up to 0, at least one is 0 and at least one is positive, at least one is negative, at least one is positive. So this generalizes to the sum of the indices is at least the dimension of the ambient space, and what you get from the other side by just taking all matrices to minus. What are the... Yeah.
So, in the case without magnetic field, one can count the change of sign, but as soon as you introduce magnetic potential...
Okay, so first of all, this is... First of all, here you see that everything is without magnetic field, but No, what Mark Gorecki and I proved is that if you have a critical point, you can count.
Because
this is exactly
quantity is real.
This is exactly what you have in the. You're looking at a different critical point where with this line, when the magnetic flux was pi,
Okay.
was half to pi, which is pi.
Okay.
And then suddenly, up to gauge transformation is real. And that's exactly what you have here. So, just to, and this is to Polterovich. So this is a bound on. This is a bound on the nodal surplus, but we actually now try to make a bound on the number of nodal domains. To extend this proof to the number of nodal domains, if we can do it, it actually can say stuff about Pleyel. The problem is that the tightness that we have, the tightness that we have, are for graphs that are very, very far from being a discretization of a manifold. So the graphs that we cook up do not look like a discretization of manifold. Okay, so continuing with our quest for some universality. So as I said, no ergodicity. Our hands are tied without our back. We want some randomness in. What randomness do we want to put? So in a minute I will give you a topological argument for why do we want this randomness. But for the moment, I'm starting with a matrix supported on a graph G, and I want to assign to it a random signing. So what is a signing? Signing it just means that I'm flipping the sign of the off-diagonal symmetrically at random. So at every off-diagonal, at every edge, I flip the sign at random. I will say that A is good if all of my signings satisfy the nodal count condition. So all of the eigenvectors and eigenvalues of all of the matrices satisfy this. I have 2 to the E signings. So I have a large number of things that I can take them random now, and now we believed that this should give us the universality conjecture, and all of the counterexamples that we could cook up were counterexamples for a single matrix, but once we started to sample the random signing at random, we got to binomial distribution. And binomial distribution is converging to Gaussian. So what we believe that if we have a random signing and the random K, if we have a random signing and the random K, then this nodal surplus should look like a Gaussian centered around beta over 2 with variance of order beta. And not only that we believe that, we can actually prove something. So we start with the complete graph. So just mean I'm talking about matrices with no zero entries. and I take any diagonal that has distinct entry and any matrix that is real symmetric with non-zero entries on the off diagonal. So this is my setting, and only I care about the diagonal that it has distinct entries. Now I take, this is a kind of an Anderson style model. I take my original matrix, I put a parameter in front of my potential, and I take the parameter slowly to infinity. And what we can show is that for a large enough parameter, my matrix is good. Not only that it's good, the nodal surplus is exactly binomial for all k. And in particular, the conjecture holds. Now, the proof of this theorem is topological. So the proof of this theorem, I need a short brief on Morse theory. So if I have a smooth compact manifold, in our case it would just be the torus, and I have f, which is a nice enough function. So all that I need is that it's, let's say, twice differentiable, and the Hessian at critical points is invertible. Then for a point is a non-degenerate critical point if the gradient vanishes and the Hessian has non-zero determinant. The index is the number of negative eigenvalues of my Hessian that determine what type of critical point I have. And Morse inequalities tell me that the number of critical points that I have of Morse index k is bigger than the kth Betty number of my manifold. Now, the only thing that we care about here is that for the torus, the Betty numbers are binomial coefficients, which is very nice. It means that if I can show that my eigenvalues, my eigenvalue, which is now a function on a torus, on a beta dimensional torus, if I can show that my eigenvalue is a Morse function, and I can show that it has only 2 to the beta critical points. So again, for a torus, each one of these is, for a beta dimensional torus, each one of these is beta choose j. The sum of beta choose j is 2 to the beta. So this is the least amount of critical points I can have. If I have exactly the least amount of critical points, then this is an equality, not an inequality. So if I can show that my eigenvalue is a perfect Morse function that has only 2 to the beta critical points, then it has exactly beta choose j critical points of index j, which means that the index for a random critical point is distributed binomially. And this is a topological proof for a random question. Together with Goretsky, we show that any critical point of these eigenvalues is either one of these special points. So for each one of these special points, the matrix that I started with becomes real. So these matrices for different alphas are Hermitian, but only for these points they are real. So these are the fixed points of conjugation. So if I take conjugation, eigenvalues don't change, but matrix change unless I'm on a fixed point. So all of these fixed points are critical points. So I have 2 to the beta critical points. And if I don't have any other critical point, then I won. So my mu k of alpha is either the critical point is here, it's one of these conjugation fixed points, or it fails the nodal condition. So either I get multiplicity, I have 2 level sets two energy bands that collide, or I have an eigenvector that vanish at some vertex. There's a whole paper that Goretsky, Berkolayko, and I wrote about this question, and there's an Invenciones paper of Berkolayko and Zelenko about this question: what happened to the topological quantities when this is when this is a multiple eigenvalue, and when we wrote about what happened to the topological quantities when when we have some set of zero vertices. Interestingly, when we have set of zero vertices, it's not critical points, these are critical manifolds, and we can read off the most data, but it's much more complicated topology. But the conclusion is that if my mu k alpha satisfy nodal condition for all alpha in my torus, then I have binomial distribution for a random signing. So a priori, we were pretty convinced that these things should generically be Gaussian. And another convincing was that we managed to prove a similar theorem as in the quantum graph case. Only here we couldn't use the independent flip coins trick, and we had to go around and prove the nodal magnetic theorem, but not on the entire torus, only on one skeleton of the torus. Complicated, very nice, I don't have time to talk about it. The problem is, before the problem, so quick back. Our first conjecture was that for a single matrix, we have Gaussian nodal surplus around beta over 2, false. Then we said, okay, so if you give me a nice matrix and you choose the signs at random, it's going to be close to Gaussian. And we have a very nice evidence in favor until we decided to check what happens for random matrix theory. So now that we have the machinery to ask for any matrix, what is the nodal count, let's ask what happened to a random matrix. So the first thing that we did, or the only thing that we did, we wanted to touch base with GOE random matrices. That's when you have a random matrix, when you ask something about matrices, the first thing that you ask is what happened to GOE. And then we realized that the only thing that we use for GOE is that they are invariant under orthogonal conjugation, which essentially means the eigenvalues are determined by something, but the eigenvectors are chosen at random. And you would kind of guess that if the eigenvectors are chosen at random, then the statistics of the nodal changes should look Gaussian. However, this is really not the case. So with high probability, the nodal count, so to first order, the nodal count is just half of the edges are flipped. But to second order, with high probability, it is concentrated around quantities that are given by the eigenvalues. So this means here we just took this distribution and sampled the spectrum for this distribution and sampled a random orthogonal matrix and conjugated by. We got a matrix. This is not ranging over a lot of samples. This is a single sample. A single sample. This is very, very concentrated measure. A single sample of this thing for a matrix which is 1,000 about on 1,000. And this is the histogram of the nodal count. So you would agree with me that this is not a Gaussian. I usually call it the three-humpback camel. So is this in problem with this? Well, do we have an orthogonal ensemble, an invariant orthogonal ensemble for which the signs are chosen at random? Yes, we only have one, GOE. So if I sample A from a GOE, it means that choosing randomly the signs afterwards is still GOE. Which means that the nodal surplus of my sampled matrix, so, and again, remember that nodal surplus is my nodal count minus k minus 1. However, my terms here are of order, this is of order n squared, this is of order n to the 3 halves. It's much larger than n, So so going from nodal surplus to nodal count is just a lower order term, and this thing up to a lower order term is a semicircle. In particular, this disproves the conjecture, and we were extremely surprised by that. But we actually saw something different. We realized that here, all our proof didn't need to take k at random. It was binomial for every k. And here, for every k, we have a certain average, but the fluctuations around that average always look Gaussian. And we understood that what we actually need to ask is whether when you sample at a random signing for a given k, it's close to Gaussian as beta goes to infinity. And we ran a lot of simulations. Here we're taking GOE for n from 2 to 5 to 2 to 13, and it converges beautifully to Gaussian per k. And we take a uniform bound on k. This is the same question for random regular graphs. 5 regular graphs for n from ranges from 10 to 42. And again, a beautiful convergence. So we are now more convinced that this might be the right question. And now for the last piece, I know that I'm running out of time. In fact, I'm at 1 minute over. So just for the last piece, and I want to finish with a nice animation. This is a work in progress. So now we have something weird. So we know that if A is a GOE, then we know that we have a semicircle nodal count. However, we know that if we add a very, very strong diagonal, we have a topological proof that says that it's going to be a Gaussian. So we have on one hand here we have a probabilistic proof giving us GOE. On the other hand, if we add a very strong potential, we have a topological proof that gives us a Gaussian, and we're kind of wondering what happens in the interpolation in between. So this was one of the first, if not the first, models of phase transition for random matrices, the Rosenzweig-Porter model. As a cute remark, it was a model suggested in 1960 to see the phase transition in gap distributions. So this is 4 years after Wigner was talking about gap distributions, 2 years after Anderson, completely unrelated, talked about Anderson localization, and several years before Dyson got into the business. So it's really one of the first models, and you're taking a random GOE matrix, you take a random independent potential, and you take a parameter. The right scaling of the parameter is taking n to epsilon. Epsilon goes from -infinity to infinity, and epsilon equal to half is the critical value. And here's what happens. So we start with the well-known gap distribution of GOE, and at epsilon equal to half, this becomes the gap distribution of Poisson point process, and our semicircle, exactly at the same time, goes from a semicircle dictated by the eigenvalue to a Gaussian dictated by the topology. And we hope to better understand this model. Thank you.
Yeah, at the beginning of your talk, you were talking about quantum graphs, and you had some numerical simulation which supported the fact that as the graph becomes larger, the nodal defects tend to go. Yeah, but here, so you are only considering graphs with bounded degrees, are you?
No, random Ernest graph. So complete graph, random.
Oh, sorry, I
random
hadn't seen
training,
the complete graph. Okay, it was also a complete graph. Sorry, I
all of
hadn't
them.
seen this one. Thank you.
And you see that all of them kind of sit on the same curve. That was very surprising for us.
Thank you.
And again, when you're looking here, at every point, you're not looking at a single quantum graph, you're looking at the worst quantum graph for this combinatorial graph. Because we have the way to the convexity to eliminate the edge length dependent.
Questions? So thank you again.
Thank you very much.